What's cracking, guys? This is the third video in the machine learning with JAX series, and in this one we're going to build a neural network from scratch. I'm going to be using a multi-layer perceptron, and I'm going to train a classification model on top of the MNIST dataset. By the way, I'm going to be using MNIST just for convenience. Conceptually, even if we were to use ImageNet, the code would be pretty much the same. Just for the sake of me coding this real time and this video not taking 3 hours, I'm going to be using this small dataset such as MNIST. Finally, we're going to be using PyTorch data loaders to load the data from MNIST. And the reason is JAX designers, by design, decided not to develop loaders because other libraries such as frameworks such as TensorFlow and PyTorch have already done a decent job at adding this functionality, so they did not want to reinvent the wheel. So that's in a nutshell what this video will be about, and then as a bonus points I'm gonna do some visualizations, and finally we're hopefully I'll be able to parallelize the training in the case that Colab allows me to use the TPU. If not, previous videos already explained how to do that, so that's just a bonus point. Anyways, let's start with that and structure this whole video. So first thing, we're going to do MLP training on MNIST dataset, right? That's the first thing. The second thing we're going to do is we're going to do some visualizations. And finally, the third thing is going to be basically adding the parallelization. So yeah, hopefully I spelled that correctly. So now let me break these tasks into smaller subtasks. First thing, we need to create an init function, init MLP. We need to and add the predict function. So those are going to be two things we need to do here. Whoops, to do. Whoa, I don't know how to write today. Okay, that's the first to do. The second one will be basically add data loading in PyTorch. And the third to do is going to be add the training loop, loss function, and whatnot. Maybe accuracy or something like that. So that's the breakdown of the first section of this video. Now here I'm gonna just do something like maybe visualize the MLP weights. So we're just gonna see whether we can notice some patterns, especially in the shallower layers, whether MLP learn to extract certain features which are salient, which are also like understandable and intuitive to us humans. Then I'm going to do something like I'm gonna visualize embeddings using t-SNE, and finally I'm gonna do something like visualize dead neurons if I have the time. I won't be breaking this parallelization part because that's pending, and we're gonna see whether we have time, A, and B, whether I'll have TPUs on disposal. So let's start by breaking down, solving one task at a time. So first, let me start with init MLP function. So that function should, given some configuration of the MLP network, it's gonna return the weights and biases of the network. So that's a high-level description of what I want to achieve here. Now let's go and implement the function. So we're gonna call it something descriptive like init MLP, I guess, and I'm gonna pass layer widths. So that's gonna be the configuration, and then we're going to start implementing the function here. So params is just going to be some list. Basically, we're gonna iterate through this like layer widths, and we're gonna take the in width and out width will be the names. So that's the number of neurons that comes into the layer and number of neurons that goes from the layer. And basically, I'm gonna iterate through the zipped version of this. So layer widths, and I'm gonna index it like this. So basically, we wanna start here with the 0th one and go and just exclude the last element. And here I'm gonna, oops, let me paste it. I'm gonna start from the first one and go all the way, including the last element. So hopefully you'll understand in a second why I'm doing this. And let me maybe first create the high level. Let me call the function and see how that will work. So I'm gonna have ML params here. I'm gonna call the init MLP. I'm gonna pass the list here. So first thing that we're gonna do is we're gonna add like the number of elements of pixels in the MNIST dataset. Then I'm gonna arbitrarily create some configuration. So we're gonna have a hidden layer with 512 neurons, then 256, and finally 10. So what this function is doing is, as you can see here, it starts from the 0th one, and this one starts from the first one. So that means we're gonna be fetching tuples like this. this one, and then this one, and then this one, because that will enable me to create the weight and biases we need for each of the layers. So let's do that. So I'm gonna append to params the following thing. So basically, we're gonna create a NumPy random. We're just gonna randomly sample data from the normal distribution that's gonna have a shape like this. So out with, and this is just convention. We usually just first put the out dimension here and then the input dimension. So there's gonna be, for example, 512 and then 784 here. You could do it vice versa, but it's gonna complicate things later on. So there's just a convention to keep in mind. So next thing we'll need a bias term. So that's gonna be something like this, random n, and we're gonna need just the out with because that's the bias part, right? So this should now work. Let me close this list and let me just return back the parameters here. So return the params and let's see whether this is going to work. So in order to understand whether this is correct, we can maybe use the tree map functionality from JAX. So I'm gonna just print JAX tree map. I'm gonna create a lambda function here, which is going to just return the shape of the leaf, and the leaves are going to be fetched from the MLP params, which means we're going to be taking weight and biases, these matrices here, and we're gonna be printing their shapes to understand whether this is implemented correctly. So I obviously did not import JAX, neither did I import NumPy, so that's gonna fail. So I'm gonna first import those libraries. So import NumPy as MP, import JAX, and I'm gonna run this, and I'm going to run this as well. Let's see whether this is going to work. So it's invalid syntax. Let's see what I got wrong here. NumPy random. Oh yeah, I added a closing bracket here, so that failed. Let me rerun it. Okay, so this looks correctly, I think. So we have 512 here, and then we have 256 here, and then we have 10. I'd say this is correct. So there's a couple of modifications we need to add here. First thing is if I were to just use the standard deviation 1 as the initialization, this thing is gonna explode. So we need to scale these parameters. I'm not adding any fancy initialization method here. I'm just gonna scale these like this. Just gonna basically make the standard deviation smaller by a factor of 100. And that's it. The second thing we need to add here is now that we have implemented NumPy's random number generator, so we'll actually be using JAX random number generator. So that's why I'm gonna just do that right now. So it was easier for me conceptually to first start with NumPy. Now I'm gonna just quickly change this. So I guess JAX random PRNG key or something is the functionality. I'm gonna add a seed here. Whoops. I'm just gonna add some constants here. So seed is gonna be 0. I'm gonna be using seed here, and I'm gonna pass RNG inside of the init MLP function. We need to add it here as the argument. And now the thing we need to do is create the keys out of the this generator. So this is actually also a key. So I'm gonna rename it because it will be misleading. I'm gonna pass the key here. And from the key, I'm gonna create keys using the split method. So I'm gonna create keys using JAX random split method. And I'm gonna pass in the key, and I'm gonna set the number of keys to whatever the number of layers is. So that's length of this thing minus 1, right? Because the number of layers is by 1 smaller than the length of this configuration file, because we're taking tuples, remember. So this, and then finally 256 and 10 as the last layer. So that's gonna be the number of keys, and now we are going to additionally add to this zip function. I'm gonna add the keys, and I'm gonna then add the key part here, and finally I'm going to split it additionally into the weight key. So we need to split it into weight key and bias key, so something like this. So I'm gonna do again JAX random split, and I'm gonna pass in the key, and that's gonna split. Let me see whether this is going to create a problem, because this thing, I'm gonna call this the parent key just for the sake of avoiding some bugs here. So parent key here, I'm creating keys and I'm iterating through the keys here. I'm splitting them into the weight key and the bias key, and finally we're going to now input the weight key and the bias key and create the correct random function from JAX. Not completely sure about the syntax here. I'm gonna just try something that makes sense, and then I'm gonna search if it doesn't work. So JAX random, something like that, and then I'm gonna pass like the key. So I'm gonna pass the weight key, and then I'm gonna pass the shape here. So this should be the syntax, and then here I'm gonna again do JAX random, and I'm gonna pass the bias key here, and the shape is going to be something like this. So this should now work. Let me kind of split this into two lines so it's more readable. Let me kind of try and refactor this a little bit. Something like this, and then I'm gonna indent this a little bit more. Fuck my life. Okay, and I'm gonna do it like this. Okay, this looks a bit better. So hopefully this works. Let's see whether it makes sense. We have the parent key. We split it into multiple keys here. We use those keys, so we'll have a key per layer. Every layer we have a specific key, and then we do an additional split because every layer has weights and bias. We pass the weights, we paste the bias, and that's it. This should now work as expected. Let me try and run it. Hopefully it's gonna work. And it's not working because a module object is not callable. Let me see what have I done here. I called random is the module, not the function. So let's see how the actual syntax looks like. JAX random, random, I don't know. Let's see whether this is going to... Yeah, this is the wrong file. Let me try and see whether we have some interesting information here. So we have random uniform here, but do we have random something that's not uniform generator? Because uniform distribution is not as good for parameter initialization as Gaussian, because Gaussian tends to, because of the mean zero, we're gonna have an expectation smaller weights than using uniform, I guess. And also it's gonna be symmetric around zero, that's important. So I really need to find the actual Gaussian random. Let me just use something like this. Gaussian, JAX random Gaussian. Will this work? Let me open up a couple files here. I think we saw this one. Okay, let me see whether I can just grab a number from here. Nope. Random seed, random uniform. They're just using uniform numbers all the time here. What's this? Oh, random normal. Okay, this is the syntax. Random normal. Whoop, that took some time. Okay, JAX random and then dot normal, and that's gonna work. Random dot normal, and hopefully now this will work as expected. And it seems it does. Everything looks correct here. I think we are good to go to the next section. So we have the correct scale, we have the correct structure, 3 layers, every layer has weights and every layer has bias. We've used JAX's pseudo-random number generator, and we had some primitive initialization scheme here using the scale parameter. Now let's do the second part, and that's the add the predict function. So now that we have this, let me just add another cell here. Let me add a function called MLP predict. We're gonna pass in the parameters of the MLP, and we're going to what else? We need some data, so let's pass in the input data here. This is going to be a single image and a flattened one because we're using an MLP. We're not using a convolutional neural network here. So how we're gonna split this is we're gonna take the hidden layers here. So maybe let's call this yeah, I'm just gonna do it like this. So hidden layers, I'm gonna take the params, all the params except for the last one. That's gonna be the hidden layers, the first 2 layers, and then I'm gonna iterate through those layers. So I'm gonna just iterate like this. We're iterating through the hidden layers and taking the weight and bias matrices. Then we need to set activation, something like this. So activation is going to be initially equal to whatever the input is, and then we're just going to reuse it here. So activation, I don't know how to spell today. Basically, this is going to be what? We need to do activation function, and we need to create the mapping. So mapping will be basically JAX, I guess, dot product. No, I'm gonna add the JAX NumPy API here. So I'm gonna add JAX NumPy as JMP because that's gonna be useful. I'm gonna rerun the cell, and finally here, so JMP dot should work. I'm gonna pass in the weight and then the example, and then I'm gonna add the bias term. So this thing should be this is the functionality of the linear layer. And finally, we need the ReLU. So I think NN contains the ReLU unit. Yep, it does. So something like this should now function, and this should not be X. This should be activation. Okay. So this should work. Let me see whether it makes sense. So we're doing a dot product, we are adding the bias, we are doing the activation function, and we get the activation out. This looks reasonable. Let me now do the final step. The final step is we get the last and the last layer's weight and bias. So something like this, params of the last element of the last layer, and we do apply this again. So I'm just gonna copy paste this. We're gonna copy paste this. I'm gonna use the last one. The reason I'm doing it like this is because the last layer does not have the ReLU activation. So these are going to be just logits. And we could alternatively do it in a single for loop. But then I'd have to have a switch statement, like if last layer, then apply ReLU, otherwise don't apply ReLU. So at the end, it's gonna be even less readable. So I'm just gonna do it like this. And finally, we're going to return what? We're going to return logits, but not quite, because JAX does not have cross-entropy loss implemented. We'll have to be resourceful here and create something that's going to be maybe confusing at the first point. We're going to be importing from the JAX SciPy, I think, special. We're going to import something called like xlog sum or something, xlog sum. I don't know. Let me try and search for this. Not completely sure. So yeah, log sum exp, log sum exp, log sum exp. So this thing is gonna allow us to implement a numerically stable version of cross entropy. So what this is the following. So imagine we have 10 outputs, right? We have 10 outputs from the this MNIST MLP model, and let's take a single one. Maybe the single output will be called O1. So this is the raw output from the logits, and we can equivalently represent this without changing anything like this: log exp of 1, because these two are just inverse of each other, so this thing is equivalent to this thing here. So now, what this will do is it's gonna add a log sum, so it's gonna do something like log, and it's gonna have a sum of exponentials. So something like this, O1, and then it's gonna have, obviously, because it's a sum, it's gonna have as a second argument the second output, and then the third output, and you get the point, all the way through the last one, so O10. So if you just look at this expression now, let me just kind of copy paste it here so that it's more visible. And now we're just going to apply the simple rule. Basically, if you try and subtract the logarithms, it's equivalent as if you were to take the arguments and just divide them. So we're just going to take this argument here, so the left argument, and we're just going to divide it by this sum here of all these basically exponents. And you can see that this is pretty much, we just implemented softmax. The only difference is that we have log softmax, and that's it. So this is what this thing implements, and that's going to be super convenient a bit later. We're going to see why in a second, but let me now test this function as well. So as you can see here, every time I write a certain module like this init MLP, I test it here. So this is a not that rigorous testing, but some testing nonetheless. So let me try and pass some data here. So I'm gonna just create a simple dummy like image here. So dummy image flat, I'm gonna call it that way, and this is going to be ran then. Basically, again, it's going to be mp_prod of the MNIST image size. This should work correctly. Let me just print the shape to make sure this has the correct shape. It should be a flat image. So 784 should be the shape. And we're going to pass that into the MLP predict and see what we get as the prediction. So prediction is going to be MLP predict. We pass the MLP parameters we generated up there. We pass it here. We pass in the image here. So something like this, and this should now work, hopefully. So I'm gonna just print out the prediction shape here. So let me try and run this thing. So name log sum exp is not defined because I have not rerun this thing. Whoops. Okay, let's see what's wrong here. Let me reopen the tab here. JAX SciPy special. JAX SciPy special. Aha. From JAX SciPy special import. Yeah, I'm really bad today. Okay, let me try and rerun this again and see whether it works. It does not, because unsupported operand types, blah blah blah, device array and function. Okay, something went wrong here. Let me see what. So I'm passing the mp_prod should give me. So how you debug this is you just open up another cell here. I'm just gonna do it like this. I'm gonna just print out the mp_prod of this thing and see whether this gives me the number. And it does. So this thing returns back the number. And for some reason this is not working. Okay, I got it all wrong. This thing actually worked. The problem is here, and I even have the red squiggly line. I'm stupid. Basically, I just subtracted a function from this. I need to pass in the logits here, and now this should work, hopefully. Okay, and it does work. So the shapes do work as expected. So now, because this is JAX, without re-implementing this function for the batch of data, we're just gonna wrap it up into VMap, and let's see whether that's gonna work. So I'm gonna create a batched version. So batched, whoops, let me zoom in again. So batched MLP predict is going to be equal VMap, and then I'm gonna wrap the MLP predict here, and then we're gonna specify the in-axis. Let me import VMap so that I don't forget. So from JAX import, we're gonna need JIT, we're gonna need VMap, and we're gonna need PMap and grad as well. So let me rerun this, and now let me continue here. So in-axis is gonna be none, because we just want to broadcast the parameters, and it's gonna be 0 for the because we have the batch dimension will be on the 0th dimension. So this should now work. I think that's it, and let me try and test this function again. So again, let's test it. Small test here. Basically, I'm gonna create this same thing, except that this time I'm gonna add a batch dimension of 16 here. Let me check the shape here. So this is gonna be images flat, and I'm gonna pass that into the batched version and see what the predictions are. So predictions, batched version. We pass in the, again, MLP parameters. We pass in the images flat. And if I were to run this, I'm gonna just print the predictions shape, and I'm gonna comment out this first test here. So this should now work as expected, hopefully, and it does. So we get the, oh, I forgot to actually use this version of the images, so this should be 16, yeah. So this seems to work correctly, and that means we have done the first part here, and now let's jump to adding the data loading functionality. So I'm just gonna annotate this like this. So this was a small test, and this thing, these things here were also tests. And finally, okay, let's add another cell here. We need to add the data loading. So first thing, we need to add the MNIST dataset, and then we'll need to add the data loader, which is going to load the images that we're gonna pass into this MLP. So let's start with the syntax: PyTorch dataset MNIST. I'm gonna search for it. and let's see how the syntax goes like. So basically, Torch Vision datasets, MNIST something. Let's see some example whether they have MNIST here. They do not have MNIST. Let me see whether I can type something in like Torch Vision data sets MNIST example. Okay, let me return back here. I think this is going to work. I'm just gonna copy this thing. Let me put this tab here. I'm gonna need it probably a bit later. So something like this should work. I'm gonna import here. So import. So from these datasets, I'm gonna import the MNIST dataset, and now I'm just gonna be using MNIST. So I'm gonna run this. Hopefully this import will work. Let me see. Okay, it worked. So now I'm gonna use MNIST here. Basically, let me delete this, and I'm gonna create a train dataset by calling MNIST and passing in. Let's see what the arguments here are. So we have root, that's where the data will be downloaded. Then we have the split. I'm just gonna leave this as the default one. Train, download, and transform. So, okay, it sucks that it doesn't have an example here that I can just copy paste. So let me just do it like this. So we need root, we need basically split, we need train, download, and transform. Those are the four we'll need. So root is just gonna be basically the structure, how it looks like is the following. So if I was to add an additional cell here, import OS package and print the OS get current working directory, it's gonna print content. So this thing here is called the content directory. So I'm gonna, inside of this directory, I'm gonna into the I guess train MNIST, I'm gonna download the train dataset, and we're gonna need what else? We need the train equals to true. So that's gonna make sure that this is the training dataset. And finally, we need download and transform. So download, I guess download is by default true here, right? So download, if true, downloads the dataset from the internet and puts it into root directory. If dataset is already downloaded, it is not downloaded again. So yeah, we want to download it, and then transform is going to be needed as well. We're going to see why in a second. So for now, let me just omit it. I'm just going to put transform to none, and that's it. Let me just print the type of this thing, train dataset, just to have something as a placeholder. And let me rerun this. Let me close this. Let me rerun this and see whether this works. And it does. It's downloading the data. I think it finished. We have train MNIST dataset right here in this Google Colabs storage space. So let's now analyze what this dataset is. So basically, if I were to fetch like a something from the train dataset, so I'm fairly sure it has the index functionality, so I can just index and take the 0th one. I'm gonna print the type of this something, and that's going to be basically, as you can see here, pill image, and we have a label. So that's the structure of our dataset. So because we're working with JAX, we're now going to be using PyTorch tensors. So that means we need to convert this into a NumPy array and not pill image. So how do we do that? And the answer is using this transform functions. We're just gonna add a simple transform function. So I'm just gonna call it custom transform. And what the function is going to do is it's gonna take the image and it's going to convert the image into NumPy. So something like this. So NumPy array of this X, and I'm just gonna set the data type to mpfloat32, and I'm gonna return this thing. I don't even need a temporary variable here. So just return this. And now if I were to run this, let me see whether it's gonna be converted into NumPy. And it's not, because I forgot to add the custom transform here. So let me run this now, and yep, I'm getting unveiled the output here, which is a good sign actually. So let me, instead of printing something, let me print the something 0 and then the type. This should be I guess, NumPy. And it is. Okay, so we got that sorted. Basically, we now have a NumPy float32 image. And the second, let me just check what the second part of this something tuple is. So let me just check whether that's integer or whatnot. So it is, it's an integer. So we have, because it's a label. So I think that should be all right. Now we need to additionally create a test dataset. So I'm just gonna copy paste this part here. I'm gonna copy paste it here. This is going to be a test. Train is false because we want a test dataset. Download equals true is okay, and custom transform, that's all okay. So let me just run this again and see whether it's all right. So it's downloading the test data, and as you can see here, we have the test MNIST in the storage space. Okay, cool. Second thing we need to do is add the data loader. So we need to be able to load these images in. I think I just understood is I made a mistake here. We need to flatten out images. So if I were to, again, if I was to take the image label tuple, because I know what this is now, I'm just gonna take the train data set, I'm gonna take the 0th one, and I'm just gonna take the, actually just, let me just grab the image by adding 0 here. This is an image, but the thing is, the shape of this image is, I guess, 28 by 28, yep. So we need to add the, just flatten the function, flatten the thing here. And if I were to run this, we get the correct shape now. So this is now correct. Basically, the last thing we need to add here is just a data loader. So if I was to search it, PyTorch data loader, let's see what I get here. Data loader. Okay, we have the signature here. I'm just gonna copy paste it, and let's see whether that's gonna work for us. So I'm gonna obviously need to import the data loader functionality. So let's see, where can I import it from? Torch Vision or whatnot, I don't know. Let's see here. Import PyTorch data loader. Let's open up this data tutorial. So basically, data loader. Oh my god, I hate this. Okay, from Torch utils data, import data loader. Okay, let me go back here. Let me import that part. Let me rerun the cell, and now we have the data loader. Okay, so this will work. I'm gonna use the train dataset. I'm gonna create the train loader, and I'm gonna add some random parameters here. So batch size will be set to, for example, 128, and so just pass in the batch size. Shuffle is gonna be equal to true because this is the train dataset. We wanna shuffle. We don't need the custom sampler. We don't need a batch sampler. Number of workers is not important. We'll need a collate function because now we have a, basically we're not using PyTorch tensors. These are all just optimization parameters such as pin memory, so we don't need none of those. So let me just do it like this. So we additionally need to create a collate function because let me see what happens if I were to just use it without a custom collate function. So batch of data is equal to next. I'm just gonna convert the train loader into iterator and then just fetch the next batch using the next function. Let me see what this thing is. Batch of data and whether it's gonna work. So it's a list. Okay, let's see what this list consists of. So if I was to take the 0th element and run it again, it's a tensor. So as you can see, PyTorch by default creates a tensor if we do not add the custom collate function. So that's why I'm gonna add a custom collate function here. So def custom collate function. We pass in the batch of data. Basically, we want to have all of the images batched into a single NumPy array, and we want to have all of the labels in a separate data structure. Let's see what we currently get. So I'm gonna just grab this custom collate. I'm gonna paste it here. So this batch input is just going to be a list of tuples, and each tuple contains the NumPy image and contains the label. So we need to convert that into a bit different shape. So instead of having a list of tuples, we need a list with two elements. One is all of our images batched into a NumPy array, and the second one is all of our labels basically inside of a single NumPy array. So just to make sure I'm correct here, let me print the type of batch. That should be a list. Then let me print the type of the batch of 0. That should be a tuple. Finally, let me print the type of the batch of 0, and then 0, this should be NumPy. And if I were to copy paste this should be, I guess, integer. And yeah, this is gonna fail obviously because we're not returning anything. Hopefully the print functionality will work nonetheless. Yeah, we have a list, then we have a tuple, then we have NumPy array, we have integers. So I already knew the structure, obviously. If you did not know the structure, you can just kind of play with it, just analyze the shapes, analyze the types, etc. Okay, so what we need to do here is we need to transpose this data. So I'm gonna do it something like this. Transposed data is gonna be, I'm just going to unpack the batch of data here and then zip it. So what this will do is we'll now have, so this is a list of tuples. After we do this, we'll just have a bunch of tuples, and zip will take the first element from every tuple, that means all of our images, and it's gonna put it into a single list. And then it's gonna take all of our labels from all of the tuples, and it's gonna combine it again into a list. So we can make sure that's correct. So this again should be a list, this thing here, and basically the 0th element should be a list as well, and the first element should be a list as well. So this should be, all of these should be lists. Let me check whether that's the case. Zip is not subscriptable. Let me see what I have done. So basically, let me check. Oh yeah, I have to convert this into a list explicitly here. So let me now run it. And yeah, so we have list, tuple, tuple. So yeah, instead of a list, they're actually using tuple in the background. If I were to try and, so the length of this thing should be 2, I guess. Transpose data length should be 2 because now we have, yeah, it's 2. Because now we have all of the images and all of the labels in a single tuple. So the next thing we need to do is basically convert the tuples into a NumPy array. So I'm gonna do something like this. So labels is a NumPy array of this transpose data of 1, because the second tuple is the labels. And then we need images, and here it's a bit more complex. We need to do np stack of transpose data of 0. And this will hopefully work as expected. Now I'm gonna return back the images and the labels, and this collate function should now properly work. Let me run this and see whether we have the correct result. It seems nothing is crashing, so I managed to get the batch of data. We're printing the type, and it seems, okay, it's a NumPy array. Let's see what the shape is. So if I was to take let me do it like this. So batch of 0 are images, so that's like this, images, and oops, and finally let's see what's the shape of the images. Let me delete this thing and run this, and yeah, we have a batch of 128 images which are flattened out. And if I was to take the labels, same as this here, I'm just gonna add instead of 0, I'm gonna put 1 for labels, and let's see the shape of these labels. This looks correct. And finally, we need to check the data type. So images, let's take the 0th image and print the data type, and also let's take the 0th label and print the data type. So it's always a smart idea to understand your shapes and your data types to avoid some bugs down the road. So float 32 looks good, and in 64 I think that's gonna be totally fine. Okay, we have our data loading functionality. Let's continue on and see what else do we need to do. And that's adding the looping function, so the training loop functionality. Let me delete this because this is done. And let me also delete this. And let me add a final cell, adding a looping function, a training loop function. Okay, this should be fairly simple. What we need to do is define the number of epochs. So number of epochs is going to be, I don't know, for now, let's put something like 10. So we're going to iterate through the epochs. So in range num of epochs, we're going to do it 10 times. We're going to do what? So we have this pattern where we take the MLP parameters. So we have the MLP params. We're going to do some update function to which we're going to pass the MLP params. We're going to pass the data, so images and GT labels. And this should just update our parameters, and that should be the high-level functionality. So now we need to write this update function. Let's see how we can do that. So def update. We pass in the params, we pass in the images, we pass in the labels. Okay, obviously I forgot to add data loading functionality here. So we'll have basically for what? We'll have images, we'll have labels in the train loader. And now we can pass the images and the GT labels. But there is a small catch here. So images... Images are currently on a CPU, and that's going to be handled correctly by the JAX NumPy API, so we don't need to worry about that. The thing we need to do here, though, is to convert the labels into one-hot representation. We'll soon see why. So let's first start developing this update function, and then we'll understand what else we need to develop. Okay, we obviously need to call the batched MLP predict function. Okay, this one. We're gonna pass in the the parameters. That's this argument here. We're gonna pass in the images, and this will return the expected shape of this will be whatever the batch dimension is, and then 10 because we have 10 outputs. Remember, and these are log softmax outputs. So let's call those predictions. So those are predictions here. Finally, this is the trick that I told you about that will help us achieve the numerical stability of cross-entropy loss. So we'll need to just do something like this. We need to multiply predictions with these labels. So these are just GT labels, so ground truth labels. If we multiply them, and if they're one hot, that means we'll fetch the log softmax component from the predictions wherever the true value is, and we'll want to push that to 1. So we'll want to have a probability 1 there because GT label, basically says that that's where the true class should lie in. So now we just need to basically add minus JMP mean here, and this is going to work as expected because this is going to fetch the correct component, this part here. And then we just do the mean. That's going to give us this is the cross-entropy implementation pretty much. We'll later, if I have enough time, I'm going to do a more intuitive implementation. We're going to see it's not working because of numerical problems. So the final component, as you can see here, we need to convert this into one hot representation. So that means that GT labels are actually JAX. Let me see where it's in. Yeah, it's here. So basically, we just convert labels into one hot. I'm going to make sure this shape here is correct. So labels, shape, and let's see whether that's going to work or not. Okay, this is obviously a dummy mistake. This should be in a loss function, not in the update function. So we have loss function. We pass in the parameters. We pass in the, I guess, images and the GT labels. And here we need to do this thing. All of this goes into the loss function. And now in the actual update function, what we'll do is we'll take the gradients. So we'll just find the grads. So we'll call the grad function, and we'll wrap in the loss function. We're gonna pass in whatever is required. So that's params, images, and GT labels. And this is going to give us basically derivatives of every single parameter in this pi tree here. So we get the grads here, and finally we need to return the JAX tree multimap is the function I need here. We're gonna just do a simple function here. So we get the weights, we get the gradients, and what we do here is, okay, I don't need this here. Let me just do the stochastic gradient descent update here. So basically from the weight, we subtract learning rate times the gradient, whereas I'm gonna just add some learning rate here by default, something like, I don't know, 0.01. And finally, let me pass in the pi trees, so that's params and grads. So this should now work as expected. But we don't have any metrics here or any logging of whatever kind. So neither the loss nor the accuracy. So I'm just gonna do a small break here and then a break here. Just make sure that this thing works. So 100 required 1. Okay. So I forgot to add the number of classes of MNIST. So MNIST classes. I'm just gonna pass in the length of that thing here and see whether this works now. So learning rate is not defined. Why not? I just added it here. So let's see. Oh my god, I actually placed this here. I don't know why I'm making so many mistakes. Learning rate here. Now let's try and run it. Yeah, I'm gonna expect this is gonna last a little bit. Okay, so this thing actually worked. Now let me try and grab the loss, not just the grads here. So I think the function is called val and grad. So let me just check that. Val and grad JAX. Let's see whether that's the name of the function. JAX package. Value and grad is the name of the function. Okay. So we have value and grad here. Value and grad. So that's gonna return the loss and the grad. And here I'm gonna return the loss and the parameters. And so let me just do loss here. And let me print the value of the loss, and let's see what happens here. Okay, I forgot to obviously import this thing here. I guess it's from JAX, right? Yep, it seems that's correct. Let me run this, and we get some reasonable value of the loss function here. So that's cool. Let's now try and remove the break. And let's run this for a single epoch and see whether the loss goes down. So let me run this and see what we get. So it seems that the loss is going down, and that's very, very reassuring. The only problem is we're getting too many output here. So let me just interrupt the execution here and let me clear this output. Wow, there's so many. Okay, let me just clear this. I'm gonna add a conditional logging here. So if I'm just gonna place enumerate here so that we know the batch ID, so something like this. And if the counter, so because every batch has 128 images, let's say we can log every 50 batches or something. So if this equals 0, finally let's move the loss inside of this if statement. So let me indent it here. I'm gonna also just print this thing once, and now this looks like it should work. Let me run it and see. So 128.10, this looks to be a good format. So I'm just gonna interrupt this execution. I'm basically going to just leave the loss printing here. And the final thing before I'll remove this break is to add the accuracy metrics. So let's add the accuracy logging as well, and then we'll be certain that the MLP is learning something. So accuracy, again, I'm not sure whether JAX, let me see whether JAX has accuracy metric. Yeah, I don't see anything, so I'm just gonna implement it myself. So basically, we're gonna pass the parameters again. We're gonna pass the loader, so either a test or train loader, and that should be it, I think. So the thing we need to do is find the number of correctly classified like images. So I'm just gonna basically iterate through images and labels. Here in the loader, I'm gonna again run so I'm gonna call the batched, so something like this. I mean, this is going to be inefficient because I'm gonna run it in general if we had some arbitrary data set. But this implementation is gonna work for MNIST pretty well. So I'm just gonna go through the whole training set and through the whole test set and find the accuracy and report that somewhere here. So after we finish the epoch, I'm gonna print like something like this. So epoch, and then I'm gonna print the ID of the epoch. And then I'm going to print the train accuracy equals to this, and test accuracy equals to this. I'm just going to call the basically accuracy. I'm going to pass the MLP params after the epoch has been finished. I'm going to pass the train loader, so this thing, and I just forgot to, so I basically just realized that I forgot to add the test loader, so I'm going to quickly add that as well. So something like this. Let me paste it here. So now I have to add the test loader somewhere above. Let me see where I've defined. Yeah, here. So I'm going to add the test loader. It's going to be the same as the train data loader. I'm just going to swap this for test data set. Batch size, I can leave it the same size. Shuffle, false, no need to shuffle the data set, and custom collate function is also fine. So I'm going to rerun the cell, and now we have the test loader. So this should now all be correctly set up. We just need to implement the actual accuracy metric here. Let's see, we need to do the same thing as here. We need some predictions. And then I'm going to find the basically, instead of finding the raw predictions here, so the log softmax, I'm going to do immediately call the soft argmax function, and the axis should be 1. So that's going to find the highest probability class for the particular prediction, and we're going to get basically prediction classes here. And we're going to contrast that with labels pretty much. So we need to do something like this. We'll need some temporary variable, so I'm gonna call it accumulator. Basically, accumulator is we're gonna add here the MP sum between which is gonna do predict classes, and we're gonna see where those predicted classes are the same as the ground truth classes. So I can maybe do something like this just for consistency sake. So this, and we're gonna sum them up, find where we had true. That means we had the same class, so this is going to work correctly. And finally, in order to return the metric, we need to just divide the accumulated value with the length of the actual data loader, I guess. Well, is that correct? No, it's not, because we have to also add we care about the number of images. So I guess we need to multiply that with the batch size. So let me see whether loader has batch size variable. I'm not sure whether this is going to work, whether Colab autocomplete is just tricking me here. But this should work. And this may be misleading because this is not the accuracy, this is just the accumulated value. So I'm just going to replace this with something like xsum. And yeah, this is my find and replace method for Google Colab. Okay. This should now work, I think, aside from this thing maybe not being correct. Let me try and run this. Maybe instead of waiting for the whole epoch, I'm just going to run it right at the beginning here once. Let's just see whether this is going to work. Okay, this actually failed, and the reason is already quite familiar to me from PyTorch. So what I forgot to do is basically we have to set the drop last to true here. Otherwise, we'll have so potentially the last batch will not have 128 images, and that's where the discrepancy comes to be. So if I were to rerun the cell here and then start this thing again, now hopefully we'll get the correct results. So basically what happened here is at one point the last patch was smaller than 128 and there was a mismatch doing a comparison here, and that's why it failed. Here you can see it's now working, but the thing is it's very, very slow. So what I'm going to do instead is I'm going to interrupt this and I'm going to load the whole MNIST into memory, because it's a fairly small data set with only 50K, 60K images. So I'm going to do the following. I'm going to change my implementation of accuracy. So instead of doing the loader thing and then iterating through the whole dataset, I'm just going to pass the dataset itself. And that means this is going to change a lot. So I'm going to just do the following. Pass the whole dataset all at once into the MLP predict. So I'm going to do something like this. Params, the whole dataset. So actually the images. So these will be dataset images. I'm going to pass them here. We're going to have the JMP argmax alongside axis equals 1. So this will give us the predicted classes. And I'm also going to pass, obviously, the dataset labels. So, and I'm going to compare those two and return the mean. So basically JMP mean of this comparison. And this is neater implementation, so it's more concise, and it's also way more fast compared to the last one. So let me see whether this makes sense. So I'm doing inference on the whole data set, and I'm then converting my raw outputs, so the log softmax outputs, into the actual class indices here, and I'm comparing them to the ground truth and finding the mean. Okay, so this looks like it should work. So now I have to do the following thing. So I have to load the whole thing into the memory. So I'm going to do the following. I'm going to take this thing. So train images. There is this internal member called data. I'm going to fetch it. That's going to get me the images. I'm going to convert this into JAX NumPy array. And I'm going to reshape this into... Wait, let me check what this will return. So this will gonna be print train images shape. Let me see what this is going to return. So yeah, as you can see, the problem here is it's avoiding. So this transform is not being called when I just fetch the data like this. So we still need to flatten out the images. So I'm gonna do that. I'm gonna just reshape this into basically whatever the length of the trained data set is, and I'm gonna put -1 here, so that's gonna hopefully flatten out the whole thing. And now, yeah, now we have the correct basically shape. Let me just check the type. Train images, it's gonna be on the device, so that means whatever accelerator I'm using, it's gonna be on that accelerator. I'm currently set to using none, so yeah. Because MLP is a fairly simple model and MNIST is a super small data set. Let me now do the same thing for labels. I need train labels. I'm going to do the same thing here. I think so, at least. So I'm going to, this time I'm going to access targets, so that's labels. I'm going to convert them into JAX array. I don't think I need the reshaping, so let me check the train label shape. And let me check the type of the train labels. So we have device array 60K. This looks correct. I think this is going to work. So we need to do the same thing for test dataset. Let me just copy paste this, replace this with test images, test labels, test dataset here, test dataset here. Finally, test dataset here, targets. This should be working now. Okay, cool. Now I'm going to, instead of passing I'm going to remove this line here. And here I'm going to pass the dataset and the labels. So I'm going to pass the train dataset, train images. And I'm going to pass the train labels. And here I'm going to pass basically the same thing, just test images and test labels. Again, I should have waited until I check this works. Let me just run it like this, see whether this is going to work. And it's way faster, as you can see, and the accuracy is for some reason very, very, very high already. I guess that's because we were assuming using the same MLP parameter. So I know what I have done. So I'm going to interrupt this. The thing is, I'm constantly updating the MLP param, so the state is saved here. I have to call the init function here. So we need to paste the, let me find it. Let me find the init function. We need to paste this here so that we start fresh every time we start the training. So this now looks like it should work. Let me run it. We have the results very, very fast. The accuracy is now low. That seems to be working. Let me interrupt the execution again, and I'm gonna delete this. I'm gonna, yeah, this now should work. We're logging the loss every 50 batches. We're logging the accuracy every epoch, and we have how many epochs? We have 10 epochs. So let's start with like 5. And I'm gonna run this, and yeah, let's see what the results are. So the loss is going down. That's cool. That seems to be promising. Okay, after a single epoch, we have 91% accuracy, and we do not see any sign of overfitting, because the accuracy on both training and test data sets are pretty much the same, 91%. And now we have 93. I'm gonna just skip until the training is done. Okay, the training is finally done. We have 96% accuracy. With a couple of more epochs, we'd get to, I guess, 98 at least or something. It can be further improved, but the thing is, this thing is already working. So let me just kind of clear the output, and let me try and run a prediction on a single image. And I should have done this previously. So let me fetch a single image, visualize it, and see whether the ground truth label aligns with the predicted label. So I'm going to do the following thing. I'm going to fetch the single image. So images, let me take the test loader. I'm going to wrap it into the iterator here and take a single batch. I'm going to take a single batch, and I'm going to take only the images, and then I'm going to take a single image and let's make sure that this makes sense. So image shape should be 28 by 28. Oh yeah, I have to just reshape it into MNIST image size. Let me see whether this is going to work. It is. Now let me import ad hoc here. I'm going to import just the matplotlib pyplot as plt. Plt image show the image, and let me just plot that thing. So this looks correct. We have number 7. We'll also need labels, so I'll have to modify this. I'm gonna grab labels as well. So labels, and let me check the ground truth label here. So ground truth label is gonna be labels of 0, and let me print the actual label here. Print the GT label. It should be 7. And it is. Okay, so now let's see what our network is giving us. If I was to do the MLP predict on top of a image, but I'll have to flatten it out. So I'm gonna pass the MLP params, and I'm gonna pass in the I'm gonna pass MP ravel of the image. Will this work? Let me check. So let me check whether this is going to work. These are just predictions, and yeah, we get some results. Let's now just do the argmax instead, and see what we have. So yeah, we have the predicted value of 7. So let's just add some string here, and this is GT like this. I'm gonna paste it here. Let me run this and see whether it makes sense. So predicted 7 and GT7. So I should have done this image analysis while I was developing the loaders here. So basically while I was developing these data sets and loaders. But yeah, anyways, we have it now. We see everything is working correctly. So that was pretty much it when it comes to the model training. So it was the first section. It took around an hour to do this. So now I want to do the following. I want to quickly refactor the whole code base, and then I'm going to do some visualizations. I was basically cutting some corners because I'm filming this and I'm coding real time, so it's hard to kind of be very, very pedantic. So now I want to improve some of those, some of the things. So let me see what first. So this thing, this function looks fairly nice. We have parameters here. We have keys. I think the structure of this function was fairly nice. We have this small testing functionality here, so I'm just gonna call it test. We have a key. We just called the function to see whether the results make sense, and I think this cell was neat. I was still very, very fresh, I guess. This was some initial, like, this cell was used for debugging, so I'm just gonna basically delete it. Let me see. Okay, so I had some explanations here, etc., etc. Again, the design of this function is fairly neat, I'd say. You can obviously always add some like doc strings, comments, etc., whatnot. Okay, let me see here. We had some tests here. So this was this first part was testing basically whether the MLP predict is working as expected. And so I just printed the shape of the image, I printed the shape of the output, and the second part was actually testing whether, so this test tests the single example function, and this was testing the batch, batched function basically here. Okay, I can uncomment this part as well. So yeah, I mean, it would obviously take a lot of time to create this, to make it perfect. I want to make sure that I don't have any red flags, like a huge red flags. So I defined these custom transform and custom collate functions. These look neat as well. So some consistency in my naming of the variables would be appreciated. I'm sometimes using labels, the full word, and sometimes I'm abbreviating it into LBLS. So that sucks, but yeah, this looks nice. We have the data sets here. I did some debugging here. I'm just gonna comment it out, and I'm basically just gonna delete this part. Now we have the data loaders. Then I did some testing here. So this can be considered like a testing section. Again, testing section. What I did here, I made sure that we have images, labels of correct types and shapes. And finally, this thing here is just the optimization part where I was loading the whole data set. Load the whole data set into memory. Okay. I'm gonna refactor this notebook a little bit after I finish this video, and I'm gonna upload it to my GitHub. Hopefully you saw this one already. So GitHub, let me open it up. So I have this get started with JAX repo. Do check it out. I'm gonna be posting all of these tutorials there, as well as some other useful resources and videos here. So that's it. Let's continue here. Okay, this to-do is done. We have the loss function. I'm gonna just delete this here. We have the update function. We have the accuracy. Maybe the metric and the loss should be one close to each other here. That's it. And finally, we create the network here. Create an MLP. I guess a MLP. And then we have the training loop here. Finally, I could have probably just replaced this with a product function, so to make this a little bit more robust, but this is not that robust in any case because I'm hard coding names here. But yeah, you get the point. In general, you'd have a section where you're defining these variables depending. So when the dataset changes, all of these variables change, and basically MLP is out of the box is gonna have a compatible shape. This was the point of doing this here. And yeah, you don't want to hard code stuff around your code base. So yeah, all in all, for a code that was written very, very, very ad hoc, I think this looks pretty decent. So we have the loading here. We convert the representation into the one-hot representation. Then we call the update. We do some logging of the loss. We do some logging of the accuracy, and I think it's fairly cool. Now let's do a couple of visualizations. First, let me visualize the MLP weights. So I'm gonna copy paste this into a novel cell here, And what I mean by that is the following. So I'm going to take the MLP weights. So I'm going to take the MLP parameters. I'm going to fetch the 0th layer. I'm going to fetch the weight matrix. And I'm going to just take that weight matrix and see what the shape is. So the shape of that matrix is, let me see, 512, 784. So what I want to do here is for a single output neuron, I'm gonna fetch all of the weights for a single neuron and see whether we can see some pattern, some interesting pattern. I'm gonna do something like this: weights single equals weights. I'm gonna fetch a single row. I'm gonna fetch all of the columns, and I'm gonna reshape that. I'm gonna reshape that into the MNIST image size, so that's 28 by 28, and this should now be of correct shape with W single shape equals 28, 28. I'm gonna just plot this, and let's see whether we have some meaningful results here. So I'm gonna plot it, and we do not have any meaningful results here. So if I was to randomly pick some other like some other weights for some other output neuron, like 4 maybe, I don't know. Let's see whether we can find some meaningful representation here. And I do not see anything meaningful here. I'm gonna try one more. Nope. I guess not that interpretable, but we still have 96% accuracy, so that's cool. And it was worth a try to just do this initial visualization. So this task is done. Whoops. Let me just delete this to do, and let's jump to the second one. So visualize embeddings using t-SNE. Let me do that one. I'm just gonna add a new cell here. We're gonna import basically, let me see, SciPy, t-SNE. Okay, yeah, from scikit-learn manifold t-SNE. So this will probably come in handy, this documentation here. I'm just gonna put the tab right here. What the fuck? Okay, let me put it here. Import from scikit-learn, sklearn, we import manifold module, and we import t-SNE. So from this package, from this module, import the function t-SNE. My god, okay. Okay, this should now work. So t-SNE is going to do a dimensionality reduction, and for that I'll have to fetch the activations from the MLP just before we apply the linear layer. That means we'll have to modify this predict function. So let me find the MLP predict function. I'm gonna copy paste it to this cell here, and I'm gonna modify it. So first things first, let's call it something else like fetch activations, I guess. We're gonna pass the params, nothing changes there. The only difference is we do not have to apply this this last part. So let me think. This will be yeah, we basically do not want this part. We just want to return back the activations, the last ones, just before we apply the linear layer. So activation, something like this, and this should now work. So now let me just create a batched version of this thing. So batched fetch activations is gonna be vmap. We're gonna paste this function in, and finally in axis will be again none and 0, and this should now work. So I'm just gonna fetch a batch of images, and I'm gonna get those activations, project them into 2D space, and plot those images just to see whether the MLP, the network, learned how to separate different classes. So let's see how that will look like. So batch of activations is gonna be equal to basically this, and we need to pass MLP params. So that's our trained network. And we also need to pass a batch of data. So that means, let me fetch a batch of images. So batch, I'm gonna take like this, images, labels is gonna be next, iter, and I'm going to again take from the test loader. So test loader, and yeah, this should be it. Now I'm gonna take the images, and I'm just gonna pass them here, and this should now work. Let me see, what's the shape of these batch activations if this thing works. So shape, let me run this, and it's 128 to 56. And that sounds about right, because remember we had, let me find the configuration, so it was, 512 to 56. So 256 is the dimensionality of the activations just before we project them into the logits. Okay, so let's now do the following. We need to pass this into the t-SNE method in order to get 128, comma 2. And this time I'm just gonna use my GitHub because I have this pre-existing code already, and I don't want to search through the documentation. This video is already too long. So I have this annotated get like method, and it got pretty popular. And anyways, I used t-SNE here, so I'm just gonna copy paste a snippet. Let me find where I've been using it. So here, I'm just gonna take this part and I'm just gonna copy paste it right into our notebook. So let me do it like this. Okay, so t-SNE is here. We'll take two components, means basically we want to down project into 2 dimensions. Perplexity 30 is just a number that works. We don't need the special method here. And now finally I need to pass the batch activations here. And yeah, so this is how the usual normal workflow of a guy who does machine learning looks like. You take somebody else's code or your own code, even better, and you just kind of tweak it. So also we won't need this part as well. So number of classes is going to be equal to 10 because this is MNIST. And finally, let's see, I'm just going to erase these comments for now. So the only thing we need to change here is to put labels instead of node labels here, because those are our ground truth labels. So basically what this does is for class 0, we're going to extract only those embeddings which we know correspond to images which are of class 0, i.e. have the number 0 in it, because this is MNIST. So let me change this to labels. This should all work. Now we don't need these special, I'm not sure whether this is going to work in Colab. So the only thing we are left to do is to find this dictionary. So let me find the dictionary, and it's here. So it's just a mapping from a number to a color, and let me just define it somewhere here, and that's it. This should work now, hopefully. And it does. Okay, so we can see that this is just some stupid error from scatter plot. I've already seen this error, but like it does not change the semantics, so everything works correctly here. So we can see that different classes are clustered together in a particular parts of the 2D space. We see some outliers, like there is this yellow dot here, if you can see it on your screen. But yeah, in any case, we can see that the MLP did learn something. So that's cool. Now the final thing I thought doing is basically seeing how many dead neurons we have. So I'm gonna delete this cell here. I'm gonna add a new cell just below this one. So what we need to do here is to find those neurons that do not activate on all of the input images I'm gonna feed into the network. And those are considered dead neurons because their gradients are going to be 0, which means the weights that come before that neuron output can't be changed, and thus, the neuron is pretty much dead. I'm going to link a cool article down in the description so you can check it out. It has a very thorough analysis of various activation functions, and there is a dead neuron analysis section as well, so you can check it out there. So what we need to do is, again, we need to modify the MLP predict function. So I'll have to paste this again here. So let me take it. And we'll need to fetch every single one of these activations. So let me create a collector variable here. And I'm just going to collect every single activations here. So I'm going to append activations, and that's gonna be it. We again do not need this part because we don't have rally activations here. We just care about the outputs of the rally unit. So finally I'm gonna return back the collector here, and that's it. Everything else remains the same. Yeah, combining this one with this one is probably possible, but yeah, I just decided to do it ad hoc like this at the moment. I'm just gonna name this fetch activations 2 because I'm being super creative right now. Okay, so what we need to do is basically, again, batch this one. We're going to create a batched version of the function. So a batched fetch activations to function with vmap here, and I'm going to pass the function in axis, again, none, and 0, and that's it. Now, yeah, I guess I can just copy paste all of this, and let me do it here. And now I'm just gonna need to swap this for the activation 2 version. Everything else remains the same, and we should expect to have something like, let's see whether this is going to work at all. Yeah, it's not. We're actually just getting a list here, and that makes sense because remember, that's how we are collecting the variables here, the activations here. So I actually need to do something like this in order to get the correct result, I guess. 128, 512, that makes sense. And let's see, we need to have 128, 256 in this one. And yep, we do. Okay, so now that we have these activations, now we just need to find those neurons where each of these 128 images produced like a value 0. That means this neuron was dead for all of these 128 images. And that's fairly easy, I guess. Let me form a list here that neurons. So this is going to be a flag data structure in the sense that if there is a 1, that means that the neuron is dead, otherwise it's not dead. So let's assume for now that we have that all of the neurons are dead. So I'm gonna just pre-populate this with a shape, something like this. So for act in batch activations, I'm going to, so this is going to be 100. So remember, the shape of this act will be something like 128 and then 512 or 256. So we need to fetch the shape, and we take everything except for the 0th basically dimension. And now we have for every single neuron, we have a corresponding flag here. So this is just a set of flags for every single neuron that we care about. And those are the ones that basically have a ReLU unit after them. Now let's iterate through the activations. So I'm gonna have a layer ID here, and I'm gonna have the actual activations in enumerate batch activations. So now I'm gonna do the following: dead neurons from layer ID. That's gonna fetch the corresponding structure. Equals numpy. I guess it's logical end or something. Yeah, logical end. We're gonna end whatever is here already with basically this thing, activations equals 0. So we're asking whether the neuron is dead, and if all of the neurons are dead alongside the batch dimension, then that neuron, corresponding neuron, remains dead. Otherwise, it's considered a live neuron, I guess. And I think all x is equal 0 should do the job here. Let me see whether this is going to work. So finally, we're gonna print the. So we're gonna iterate through the layers. So we iterate through the layers of dead neurons, and we print the how many of them are actually dead, something like this. Let's see whether this is going to work, and it does. So we have 0 dead neurons in the first layer. We have 4 dead neurons in the last layer. Now let's try and do something to make sure this works. So let's initialize a novel network that's not trained, and let's see whether we have different results. So now here I'm going to create a novel MLP, which I'm going to call MLP params2. And now let's use that one instead to fetch the activations. Everything else remains the same as far as I can see here. And yeah, so let me just search MLP params. Yeah, this should be it. Let's see whether we have different results here. Now a useful thing would be to actually analyze this on the whole training data set, because if there is a lot of dead neurons in the when you evaluate on the whole training data set, that may be problematic. and especially problematic neurons are the ones in the shallower layers. Feel free to play with this code at your own pace. Let me try. I'm fairly sure that I won't have a TPU at disposal currently, so if I were to try to use a TPU and click save here, let's see whether we can grab a TPU. Let me click reconnect here, and no backend with TPU is available. So in any case, I'm fairly sure that this was already super enough, because one of the previous videos I already explained how to parallelize the computation, so it's fairly trivial to make this code parallel, just a couple of lines of code, and hopefully you got something out of this video. This is the first time I'm doing a real-time coding session, so let me know if you have any feedback down below and whether you like this type of a content. So I'm gonna start making more of this if you like it. In any case, consider subscribing, share out this video, and join our Discord community. And until next time, bye bye.